All right, welcome everybody to a new week. We only have a couple of weeks left. Let's actually see how many weeks do we have left here. Yeah, we only have 2 weeks left to wrap up integration and see um, everything there is to see in this last chapter, and then everything that we needed to cover, we would have. So we talked about, where's my where's my pen? There's my pen. We talked about substitution as the method to help us figure out how to reverse engineer the chain rule in finding antiderivatives, in figuring out the integral, the indefinite integral. And originally, if we had an example, coming off a weekend, we maybe need to remember how we did this. Um, Originally, if we have like 2x, x squared plus 1 to the power of, I don't even care, like 100, then we could guess and check and say, yeah, okay, this one's simple enough. I see the bracket squared. I know it's going to have to be x squared plus 1, that bracket to the 1 more, and I'll correct it because it's the power rule in reverse. But now if I take this as a derivative, I have to follow that, the chain rule says, with the derivative of the inside function. And the derivative of the inside function is 2x, and that is exactly there as well. So I finish it with a plus c and I'm done. Now I can imagine that in more complicated situations, this guess and check strategy is going to be problematic sometimes or less reliable. What can I do? Well, that's where the method of substitution comes in to help guide me through the process by saying, let's rewrite this integral by using a different variable. We'll call it u. Most books do that, but you can call it whatever you want. And I'm going to let u represent the inside function, which is usually uh, fairly straightforward to recognize. Then it's a three-step process on the side. I take the derivative of this u function, which is 2x, and so I separate the differentials, which doesn't break any rules, and this now tells me how to rewrite this integral to not have any x's, all u-related things. So the bracket to the power of 100 becomes u to the 100. The 2x and the dx, this last line says, I have to see both of them to swap them out for a du, which I can. And then I am just in a basic reverse power rule situation. It's going to have to be u to the 101 over times 1 over 101, of course, plus my c. Then my original variable was x. I need to go back to that. This was my choice. Instead of guessing and checking, a more reliable, systematic, confidence building choice. But it was still my choice. I need to present my answer in the original variable. So I need to go back and say it's 1 over 101. U is x squared plus 1 to the 101 plus c. I just replace it back. I don't change or simplify anything. So substitution allowed me to never really think of the chain rule directly. Whereas in the guess and check approach, I needed to think about how to reverse the chain rule, which can be a little bit tricky in more complicated cases. So I do want to understand that a guess and check approach is an introduction way of thinking that I don't want to hang on to for very long. So now the only thing left is just to see all the kinds of little variations when it comes to substitution that there could be. So let's see here. We've done some of these. Let's start maybe with a number 5. 3 over root 3x minus 5. 3 over root 3x minus 5. It's a good warm-up question. So now, I should right away recognize this as a substitution situation. Why? Because I see a function of a function. It doesn't matter what else there is. It doesn't matter where the function of a function sits. Any sort of function of a function is going to be connected to the chain rule in reverse and therefore be a substitution situation. So I'm going to say let u represent the obvious inside function. There isn't much choice. And I want it to be simple enough so that I can find the derivative easily. But for most of our questions, it'll be fairly straightforward what the derivative then is. So I separate the differentials and I'm good to go. This then tells me what I need to see. Okay, well, the root will be replaced with a root u, so that's okay. The bottom line here says I need to see a 3 and a dx in order to swap them out for a du, and I see both of them there. So everything will have its place. So it's 1 over root u. The 3 and the dx, I do put them at the end, though you can put the du right at the top. I don't like the way it looks. So I was able to rewrite all x's to an integral in u, and that is, for our case, always going to mean that substitution was done successfully. Now, maybe I don't like the look of that. Maybe I prefer the u to the negative 1/2. The point is, I just have a reverse power rule situation where I don't have to think about the chain rule at all. My variable is u. I don't even see anything else, to be honest. I just see that. So it's going to have to be u to the 1/2 because the power rule is going to lower that. And there's no number in front of significance, so I need to catch that half when the power rule brings it out with a 2 plus c, of course. Then, after I've done that, I look back and ask myself, okay, I need to go back to my original variable. What is u actually? Oh, it's 3x minus 5. So I'll put that back in and I'm done. You can write that as a root, you can leave it, it does not matter at all. So trust the substitution method to guide you through the more difficult aspects and have them behind the scenes when you see a function of a function. As always, let me know in chat if you have any questions. Let's keep going. All we need to do to wrap this up successfully is more practice, and then we'll see what does this integral actually mean graphically, and we'll be pretty much done. There are fancier methods to find antiderivatives for fancier expressions, but the basic reversing power rule and basic properties and substitution, those are the only ones we are going to focus on. I'll make a new page. Okay, let's do number 6. Number 6 is a good one. Let's zoom in a little bit. There we go, number 6. X times e to the negative x squared. Now we have looked at this one before, but not with the substitution method, x times e to the negative x squared. So, yes, there aren't any brackets, but I see a function of a function right there. And with practice, that will become easier. So I let u represent that inside function. Then I simply take the derivative of that, which is negative 2x. I separate the differentials, negative 2x dx. And this tells me how to swap out x's and have only u's, which will be an equivalent but simpler looking integral. So I just need to check. I have this guy, which is going to become e to the u, so that's good. The third line here says I need to see a negative 2, an x, and a dx. Then I can bring in a du. I see some of that. I see the x and the dx, but not a negative 2. So in order for me to bring in a negative 2 with the x, I can't just change that, then the equal sign isn't true anymore. I have to put a negative 1/2 in front to balance that out so I didn't change anything. Now, the negative 1/2 is my price to have things perfectly set up. The substitution then says it's going to become e to the u. The negative 2x dx become du. And I'm in a much, much simpler situation, even though it's equivalent to the original. So I need to drag this negative 1/2 with me. The antiderivative of e to the u with u as my variable is e to the u, and of course my constant. Then I just need to go back to my original variable, which is a simple replacement of u with negative x squared. And I'm done. I can always check this last one, take the derivative, use the chain rule to check, and do I get my original x times e to the negative x? If I do, then this was correct. But I didn't rely on any guessing and checking when I do substitution. It's a more versatile, powerful method, tool that I can rely on. All right, we're just looking for some variation in our questions to cover everything. Number 7 is pretty much the same. I do like number 8. Let's give number 8 a shot. 1 minus x e to the power of 2x minus x squared. So at first glance, this might not even look the same. Like, but regardless, it doesn't matter. I see a function of a function in this e to the something. I don't have a choice. If substitution is going to work, it's going to have to be with u being 2x minus x squared. Now the questions for us will be set up nicely, but in general, you have to then check, am I able to rewrite everything in terms of u? If I am, then the substitution method is successful. If I'm not, then maybe it's a fancier thing in general that requires another method. But for us, we pretty much only have substitution. So if I now take the derivative, it's 2 minus 2x. And so many people now separate the variables like this. But I have to remember that I multiply the whole right-hand side with dx, so I need a bracket here. And now you can see, well, this bracket, 2 minus 2x, and my bracket, they're not the same. But they are very close in that I can factor out a 2 and have the same bracket, 1 minus x. So this then tells me the e to the something will become e to the u. Not a problem. In order to bring in a du, I need to see a 2, a 1 minus x, and a dx. Well, I see everything but the 2. So I want to bring in a 2, but I need to pay the price. This little small price allows me to rewrite the original integral as e to the u du. And I'm back to a super simple situation with antiderivative e to the u plus c, and we can finish it by going back to x. 1 half e to the 2x minus x squared plus c. Now remember that when I test this and take the derivative, the chain rule is involved, so I am going to, for the second part, find this bracket more or less after I simplify. All right, let's see what else there is. I do like, so number 9 will be very similar as ones we've done. Let us do number 10 and see how hard can it be? Or how tricky can it be for us? I have x times x plus 1 to the 5. Now, yes, you do have the option of simplifying the bracket. That's not what we want to do. That's very inefficient. We recognize there is a function of a function here. So substitution might be a way to go. And we don't have a lot of tools in our toolbox, so we're hopeful that they gave us an appropriate level question. So I go through the motions, I take the derivative, there's just a 1, so I separate the differentials, du is the same as dx. Okay, so this is my key telling me how to get this integral into an integral with just u as the variable. Everything has to go. So if I say, well, okay, I have my x there, I have the bracket, which is u to the 5, dx simply gets replaced with a du. Now what do? I have to replace all x's. Have to replace all x's. I can't have a mix. Now, if I have a mix of x's and u's, it means one of two things in general. One thing, I didn't choose the right substitution. And I need to go back and see if there is another option. In more complicated situations, there might be more than one option. The other thing it can tell me is I just didn't finish the substitution. It was the right choice. I just didn't go all the way. I still have lingering x's. So this is the right substitution, but I need to go fully all the way to everything in u. I can't have any stray x's floating around. If I notice the simplicity of the substitution, it allows me to say, or to solve for x and rewrite this as an equation x equals u minus 1, which tells me I can replace x with a u minus 1. Now it doesn't seem like I've done a lot in terms of moving to a simpler situation, but I have. Now I remember once I've written everything in terms of u, I don't remember where it comes from. I don't look at anything but this bottom integral. What does this integral, as if it's a brand new question, what does that question require me to do? If I've practiced enough, I would hopefully recognize that this requires that I multiply the u to the 5 into the bracket to get u to the 6 minus u to the 5. And I'm back in my basic properties. So the antiderivative of u to the 6 will be u to the 7 with a 1 over 7 correction minus u to the 6 with a 1 over 6 correction plus c, of course. And then I just go back and now remember, what was u actually? U was x plus 1. So I replace it. So it's 1 over 7, x plus 1 to the power of 7 minus 1 over 6, x plus 1 to the power of 6. You can, if you want to, find the derivative, some chain rules involved, simplify it, and verify that you get, that you get the original back after you've simplified it. But the chain rule gives me some structure. Let me zoom out one. The chain rule gives me some structure. So in the worst case, it seems as if the substitution, sorry, let me go back. The substitution gives me some structure in how to handle this. So in the more difficult examples, the substitution's easy, but I have these lingering x's that aren't immediately obvious in terms of how I need to work with them. I can rewrite the substitution equation to figure out how to replace them. All right, let's see what else there is. I wanted to do, just to practice this one more time, I think this is the best option. 11, 4x root 8 minus x. All right, now I should clearly see there's a function of a function, which means it's substitution time. The obvious inside function is 8 minus x, and then I take the derivative. It's negative 1 in this case, and I separate the differentials. So du is equal to negative dx. Then I see, okay, well, what do I need to do here to make this look ready for the substitution? First of all, well, I have this 4 that I'm not loving. So I'll put the 4 outside. It doesn't, according to the first and the third line, it doesn't really come into play. So it's just there to distract me. I do, however, want a negative with my dx, which I don't see. So I want a negative x root 8 minus x. I don't see, I can't just put in a negative. There's no negative there originally, so I need to balance that with another negative, which I put out in front. Then I am sort of ready. The root 8 minus x will become root u. The negative and the dx will become du, but the x is still there. That is when I rewrite my substitution equation and solve for x as 8 minus u. So that becomes 8 minus u. I have to write everything to u. Now, if I write this as u to the 1/2, I can multiply the u to the 1/2 in to get 8u to the 1/2 minus u to the 3/2. And now I'm in one of my basic reversing basic properties power rule situations, and I forget where this came from for the moment. I leave my -4 in front. Antiderivative of 8u to the 1/2. The 8 gets put in front because it doesn't really suit the 1 to the u to the 1/2 rather. It's going to have to be u to the 3/2, but I need to catch that 3/2 when the power rule brings it out with the 2/3. Then minus antiderivative of u to the 3/2 is going to be u to the 5/2 with a 2/5 correction and my constant. Now this is a way people write it when they just go a little bit too fast and forget that the -4 is multiplied to this whole integral, this whole antiderivative. So I need to apply that to everything. Technically also the c, but then I just get a new constant which I rename, so I can always have the integration constant at the end as simple as possible, which we've mentioned before. Now when I'm ready, I don't simplify this in any way. I simply go back and remember, what is u again? U is 8 minus x. So I put that in. Everything I copy, because if I try and simplify and substitute back at the same time, something sometimes gets lost. So if you wanted to simplify, you can do that now, or do that before substituting back. But unless you're very comfortable with this, don't do multiple things at the same time. Let's zoom out and have a look at this one. So I see when I look at the whole thing, it seems perhaps a little intimidating. But if I break it down one little step at a time, and I string a lot of little steps together, then I've traveled quite a long way. Let's see what else there is. I like the look of number 13. Doesn't seem like something we've seen before. Root 2 plus log x over x. Root 2 plus log x over x. All right. So regardless of how complicated the inside function looks, the inside function has only one choice, and that is 2 plus ugly log x. Sorry, this n looks very similar to a u. Let me just clarify. ln. There we go. I just go through the motions and trust the substitution steps will get me there. The derivative of this is just 1 over x. And so when I separate the differentials, I get 1 over x dx. People try and tweak this because of what they think they see. They try and look at the original question while they're doing these three steps. What you're doing, focus on that and trust that the method will piece everything together in the end. So now I see, okay, well, I'm going to get the square root of u. The x and this 1 over x perfectly becomes du, and it was actually quite simple. This is u to the 1/2, so it's u to the 3 over 2 times 2/3, something we've seen often now, and I replace it back to whatever u was, and I'm done. But with these more complicated ones, guessing and checking might get you into trouble, especially if you don't have a ton of experience. And even then, I don't feel very confident with a guess and check approach. It was a very basic first step to a more refined, more trustworthy method. We have time to do some more. 15 is nice. 1 over x log x. Seems like everything froze a little bit. There we go. 1 over x log x. I need to write better logs. All right, so now what makes these a little bit tricky sometimes without a lot of practice helping you, I don't necessarily see the function of a function that well. There are no brackets, no containing roots or anything to give it away. But I also only have a couple of pieces here. I have an x and I have a log of x. So my choices for the substitution uh, aren't that many. If I just focus on the x, then it's not going to give me a derivative with a log of x. But if I focus on the log of x, then that derivative is going to give me something with an x, a 1 over x. So I separate the differentials again. And again, while I'm doing this, don't worry about, ooh, do I see this? Should I be doing this? What am I seeing in the original question? No. After your three steps, now see, do I have the pieces I need to have? I see that, oops, not that. I see the log piece, okay, that'll become a u. I see the 1 over x and the dx, so together they are okay by this third step, third line rather, so I'm good to go. So it's going to be 1 over u du. Now I look at this integral, forgetting where it comes from. The integral antiderivative of 1 over u with u as my variable is natural log of u, plus c, of course. And then I go back and replace u with whatever it should be replaced, which happens to be log of x. So I have the natural log of the natural log of x. Definitely a kind of question that where I want to trust the substitution method and stay far away from guessing and checking. All right, with that, we've covered all the substitution examples you can see. You can look at the problem book for more problems. There's a mix of indefinite integrals in 12.4, some substitution, some maybe not. They all look like substitution, to be honest. And then we will move on to the next section, which is linking the antiderivative, the integral, to have a graphical meaning, just like let me paint the picture here perhaps. Just like when we looked at the derivative, we know that if we have a graph, let's suppose we graph our function, then the meaning of the derivative is the slope of the tangent line at some x value. We have our graph, we have our function. This is our function's graph here. Let's suppose that's our x value, slope of the tangent line. The slope is the derivative. But now if I have my graph coming from some function, what is the integral of that? What does it mean graphically? When I have my graph coming from my function, what does this antiderivative represent or tell me about the graph? That is the next question. Just before we finish, are there any final questions for today? I cannot see my mouse. Oh, there it is. All right, that will be it. Everything's frozen.